Good afternoon and welcome to our live stream, Tour of the Universe, coming at you from the California Academy of Sciences, Morrison Planetarium. My name is Ryan White. I'm the Senior Director of Morrison Planetarium and Science Visualization at the Academy. And I'm going to be your host for today's Tour of the Universe, where we take you from low Earth orbit, where we're starting here with the view of the International Space Station, out to the cosmic microwave background, the most distant light that we can see in the universe. So to do this, we're going to be using some really great and free open source software called OpenSpace, which has all of the data sets that you're going to see kind of built in. And that will give us an opportunity to look at actual astronomical data from telescopes and observatories around the world, as well as in space, and also just talk a little bit about where we are in the universe and how we have learned about our perspective on the universe around us. So, as I said, we're going to begin here at the International Space Station. You can see my arrow on the screen. I'll occasionally use that to point things out, but also to pilot around the three-dimensional model of the universe, which, as I said, has embedded in it data sets from around the world. And this is a great place to start because it's sort of a human scale. The modules for the International Space Station are large enough, of course, for astronauts. And if you can imagine spending some time in orbit around Earth, that's as far as we go out into space these days. And for a few astronauts right now, kind of stuck on the International Space Station for a while, and maybe not the career choice that you, or certainly that I would choose, but a pretty amazing view of our planet Earth from orbit, maybe a few hundred kilometers, a few hundred miles above Earth's surface. Right now, the ISS, or International Space Station, is over the ocean. So as we pull away from it, it kind of looks like it's plummeting into the ocean. That's not the case. It's just that we're pulling away from its location in orbit around Earth. And actually, just not to lose track of it, let me go ahead and actually add its orbit so that we can see where it is in its trajectory around Earth. And I'll go ahead and sort of speed up our zoom away from Earth so that we can see a little bit more of our planet. And you'll notice as I do, some of the way that the data appears in kind of sections, a little bit like Google Earth when you're panning around looking for your house. That is live stream data that we're bringing in to the software. We're actually showing you what Earth looked like yesterday because the imagery is sort of hot off the online press and allows us to show the most recent full Earth imagery from satellites in orbit around Earth, but that means that there are areas that are maybe a little less complete than others. For example, if we go up to look at the North Pole, we'll notice that, actually, let me just readjust here a little bit to make it easier to target the North Pole. But you'll see here that we actually have city lights on the nighttime side of Earth. That's from a data set collected over many years. And then you can also see this sort of absence of cloud cover here. And it's not because there are no clouds there. It's just because the satellite that's used to take this imagery hasn't covered that part of the Earth, because that part of the Earth is in darkness for a significant part of the day. Because we're in the northern hemisphere winter, we actually don't get a good view of the North Pole region, which means that the data are incomplete. And we'll run into that actually at a couple different points in the show when we're limited by our perspective on the universe around us. And because we're showing real data and focusing on showing the true sort of our true understanding of what the universe looks like around us, we'll occasionally run into the limits of our software and the data that we have available. So let's go ahead and leave Earth behind. And as we do, I'm going to actually bring up some other trajectories. I have you can just barely see the orbit of the International Space Station around Earth. But let me go ahead and add a few other lines here. Well, first of all, the line coming from the sort of upper part of the image toward Earth is the orbit of Earth around the sun, and we're just seeing the part that Earth is most recently completed in its trajectory and its orbit around the sun. And then this sort of circle around Earth is actually the orbit of our moon. The moon is about 240,000 miles away, about 400,000 kilometers. And if you want to think about how far humans have actually voyaged into space, that is as far as any humans have traveled. So when we look at a moon in the sky, you can imagine back in the late 60s and early 70s when people were actually making the trip that there were humans on another world in the universe around us. We don't travel there anymore, although we have plans to return. And that, in terms of human experience, in terms of actually physically traveling out into space, that's sort of the outer limit. That little circle around our Earth's orbit, the moon's orbit around Earth, is sort of the outer limit of human experience of the universe around us, at least in terms of boots on the ground, literally, in the case of traveling to the moon. But of course, we observe the universe around us all the time. If you know your constellations, it's a little wonky here because we can see Orion sort of tilted on its side, the 3 stars in Orion's belt, the 4 stars surrounding the 3 stars, the V-shaped constellation of Taurus, the bull. And now coming in from the left side of the image, we can see orbits of some of the other planets around the sun. So before I get too far, I want to mention 2 things. First of all, this is a live stream. So if you happen to have a question and you want to pop it into chat, we can relay those to me. I can't promise to get to everything, but we have our wonderful producer, Jackie Benita, is watching out on the chat for any questions that arise. So feel free to pop those in up as they come along. And if I can get to them, I will. And the other thing I want to mention is more on the content. And that is, as we start to traverse these amazing distances in the universe around us, I mentioned 400,000 kilometers, 240,000 miles as the distance from Earth to the moon. That's a big number, and the numbers are just going to get bigger as we travel farther and farther from home. So let me just go ahead and start using light travel time as a way of describing distance. This is most familiar when we talk about light years, the distance light travels in a year. And it's not a period of time, it's a distance. So the distance light travels in a year is a light year. But the distance that of the moon from Earth is more like a 1.5 seconds in terms of light travel time. So we can talk about the moon being 1.5 light seconds away. Light travels at a constant velocity in the vacuum of space for about 300,000 kilometers per second, or 186,000 miles per second. And that means that we can use it as sort of a yardstick. So we can talk about the moon being 1.5 seconds or 1.5 light seconds in terms of light travel time. To get a little bit farther from home, if we pull farther away from Earth, we can begin to see our representation of the sun coming in in the lower right, as well as the orbits of some of the inner planets. The distance from Earth to the sun is about 150 million kilometers, or 93 million miles. That's a lot farther in terms of light travel time. It's about 8.5 light minutes, or in other words, it takes light about 8.5 minutes to travel from sun to Earth. And the orbits of the inner planets that you can see all kind of nestled in the narrow dimension of the image, Mercury, Venus, Earth, and Mars, the terrestrial planets, are all huddled close to the light of the sun. They're all planets similar-ish to Earth. That's why we call them terrestrial planets, Earth-like planets. They are basically rocky planets with thick atmospheres like Venus or thinner atmospheres like Earth. And unfortunately, we don't have time to visit a lot of those. So I'm just going to kind of describe sort of where they are in the solar system. And then as we travel farther from Earth, we can see Jupiter's orbit come into view, then Saturn, Uranus, and finally Neptune. So the 8 planets of our solar system, all sort of majestically orbiting the sun. The 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, are giant planets. They're very different from the terrestrial planets. Instead of being rocky and Earth-like. They are more like Jupiter, which are large sort of balls of gas and other stuff, but less dense, but more massive and larger than the terrestrial planets close to the sun. Now, we've investigated those planets using spacecraft. So even though humans have only traveled from Earth to the moon, and that's less than a pixel in the image that we're seeing right now, we've actually sent our spacecraft out to explore other worlds. I had hoped to talk a little bit about the Curiosity spacecraft on Mars. Unfortunately, couldn't quite get that looking the way I wanted it to. So let me just describe some spacecraft that have not traveled to a planet and stuck around, but have rather sort of rocketed far enough away from Earth to explore the outer planets. The trajectories that are coming up now are the trajectories of the Pioneer 10 and 11 spacecraft, the Voyager 1 and 2 spacecraft, and the New Horizons spacecraft. Why these 5? Well, these 5 spacecraft are the fastest nuts and bolts objects we've sent out into the universe around us. They are traveling fast enough to escape the gravity of the sun. Eventually, these, in fact, we already call Voyagers 1 and 2 interstellar travelers because they've crossed into the distance between stars. But in fact, all of these will eventually, over thousands or really tens of thousands of years, make their way out into interstellar space, into the distances between the stars. Now, you might ask, how far have they actually traveled? We've been using our light travel time as a yardstick. So let me just go in and mention one other distance. If you think about the difference between the Earth and the moon, it's 1.5 seconds. That's maybe a quick pause in conversation. The distance between Earth and the sun is 8.5 minutes, maybe a quick lunch. And the distance across the solar system is measured from one side of Neptune's orbit to the other is about 8 light hours. So a good night's sleep. And we're projecting the trajectories of the 5 fastest spacecraft out to how far they've actually traveled to this point. And knowing that this is about 8 light hours, you can see that none of the spacecraft, or really just now, are they approaching the distance that light travels in a single day. And yet, the Pioneer 10-11 spacecraft were launched in the 70s. The Voyagers 1 and 2 in the late 70s. The New Horizons, traveling the fastest of the lot, traveling was launched in the early aughts. So after traveling for decades, these spacecraft have not even traveled, for the most part, as far as light travels in a single day. So using light as a standard distance measure is helpful. It is also the fastest thing in the universe. So it's a good way of thinking about how we can understand the universe around us. I mentioned that the distance across the solar system from one side of Neptune's orbit to the other is about 8 light hours. Well, the distance of the nearest star is more like 4 light years. So the difference between a good night's sleep across the solar system, a high school or college education to the nearest star. So as we pull far enough away from the sun, we actually brightened the sun now to make it displayed it the same way that we're displaying all the other stars in this data set. All of these are actual measured distances to these various stars. The closest star, Alpha Centauri, just sort of came into view in the lower left there. The stars, I pointed out Orion earlier. The familiar constellations of the stars are still relatively intact. So if you know your constellation Scorpius here, the bright star Antares is easily visible. And then the hazy band that crosses from the upper right to the lower left is in fact the band of the Milky Way galaxy, which we'll talk more about later. So these stars, we're currently depicting just maybe 100,000 some odd stars that are relatively close to home and relatively bright and easy to measure distances to. But as we pull farther and farther away, we'll notice that they don't maintain their configuration in the constellations that are familiar to us from Earth. Instead, We've traveled into interstellar space. We've traveled as far as light travels in a few decades, in just a matter of minutes. And that means that our perspective has shifted. The stars are scattered in unrecognizable patterns, at least for those who are not interstellar travelers by trade. So we're faced with a universe that's a little different from what we observe here on Earth. Now, one of the great discoveries of the past few decades is that many of these stars have planets in orbit around them. So just like our sun has the terrestrial planets and the giant planets in orbit around it, thousands of the stars in our nearby universe have planets in orbit around them. So these circles indicate not the orbits of planets, because those would be too small to see in this view, but these are markers that show the locations of stars that have planets in orbit around them. And we've discovered these through different methods, but what's striking is that these planetary systems are very, very different. Many of them are very different from our own solar system. So whereas we have this structure of tiny terrestrial planets close to the sun and giant planets farther away, that's not the case for many of these systems. And so as we find more and more of these systems, we're beginning to realize that there's a greater diversity of stories, basically, that lead to the formation of these systems. And that's helping us think about how planets form in general. And it's also helping us think about what it might look like for life to evolve on planets in orbit around other stars. So at this point, let's actually think about what humanity has sort of transmitted out into the universe around us. Because although our spacecraft, those 5 spacecraft I showed you earlier, Voyagers 1 and 2, Pioneer 10, 11, New Horizons, those fastest spacecraft that we've sent, they haven't traveled as far as light travels in a single day, but we've been transmitting radio signals into the universe around us for decades. Radio signals are a form of light, so they travel at the speed of light. And so we can think about what we nicknamed the radiosphere as a sort of measurement of how far our signals have traveled into the universe around us. So this is a sphere centered on the sun, and because the strongest radio signals that we've transmitted really began in the late 30s and early 1940s with the advent of television and radar, and eventually atomic tests, above ground atomic tests. Those human activities create radio signals that are strong enough to escape Earth's ionosphere and thus can fill a volume of space. Centered on the sun with a radius, so from the center out to one side, the difference between 1939 and today, if I'm doing my math right, is about 85 years. And that means that our radiosphere has a radius of 85 light years. So this volume of space centered on the sun, you can imagine as our electromagnetic footprint in the universe around us. This is as far as our radio signals have traveled out into the universe. And although the sphere is getting bigger at the rate of 1 light year in radius every year, there's a limit as to how far our radio signals have traveled. So if you can imagine that perhaps one of these stars has a planet in orbit around it with life on it, and maybe there could be a radio astronomer, someone who detects radio signals from objects in the universe, who would look for signs of life in the universe, just like we're doing as humans, looking for signs of life using programs like SETI, the Search for Extraterrestrial Intelligence. If you were one of the civilizations close to the sun, inside the sphere, you could potentially turn your radio dish toward Earth, and if it were sensitive enough, detect a signal from our planet. But if you happen to live too far away, and even if you had the right technology with the right sensitivity and all of the right things, even if you look directly at Earth, you wouldn't see a signal because the light just hasn't had time to reach your instrument. So again, we can think of the radiosphere, the sphere centered on Earth with a radius of about 85 light years, as the electromagnetic footprint of our species in the universe around us. So in a way, this actually represents kind of our technological history. The same way we can talk about a good night's sleep across the solar system or a high school or college education to the nearest star. This is, as our electromagnetic footprint in the universe, is our technological history made manifest in this sphere centered on the sun. So now, as we pull away from our location, I'm going to go ahead and get rid of, you can see some of these exoplanet markers even now. I'm going to get rid of those if that's okay. And I want to focus instead on our galaxy. I pointed out the Milky Way earlier, that hazy band of light that we see actually from Earth on a nice clear dark sky. But also we see now from the outside as we think it might look. We've never traveled far enough to check this out in person or using our own instruments. Instead, we look at other galaxies and we look at, we make measurements of things inside our own galaxy to determine what our galaxy might look like. So this spiral galaxy that we see in the upper right part of the image, now nearly face on, has beautiful blue spiral arms. If you haven't lost track of where we started, our radiosphere is just a few pixels here in the center of the image. Again, that's our electromagnetic footprint in the universe. That's our technological history, interpreted as a physical object. But look how large the galaxy is in comparison. It's actually about 100,000 light years across. So it takes light about 100,000 years to travel from one side of the Milky Way galaxy to the other. So our collection of hundreds of billions of stars and gas and dust and other stuff, planetary systems, planets in the process of formation, all of that stuff in our galaxy, 100,000 light years across, hundreds of billions of stars. If we think about that in terms of human timescales, well, 100,000 years ago, our species hadn't even left Africa. And in fact, we're about, from our radiosphere to the center of the galaxy, we're about 35,000 light years. 35,000 years ago, we were painting the insides of caves. So that measuring technique that we used, starting with a 1.5 seconds from light travel time from Earth to the moon, 8.5 minutes from Earth to the sun, 8 light hours across the solar system, 4 light years to the nearest star. Now, from a human scale, we're talking about the history of our species on the planet. And our galaxy is not alone in the universe. The sort of faint kind of red circles you can see here in the distance, as well as this object, which is a satellite galaxy of our own Milky Way. All of these are individual galaxies. The large and small Magellanic Clouds are a little bit smaller, much smaller actually, than the Milky Way. And as I mentioned, there's satellite galaxies of our own Milky Way. But many of these other sort of red dots or individual markers are galaxies as large as ours or larger. Some galaxies may have as many as a trillion stars. And as we travel farther away, we're going to make those a little brighter. And what I want to call your attention to is that the galaxies aren't sort of uniformly distributed out in space. Instead, they kind of clump and cluster together. And while we live in a perfectly nice galaxy, we don't live inside a cluster of galaxies. Instead, we live in a relatively not so densely populated part of the universe in galactic terms. This clump of points up here in the upper right is actually the Virgo cluster of galaxies, a collection of about 1,000 galaxies. By comparison, our local group of galaxies in which the Milky Way resides has about 50 members. We're going to continue to fade up more and more galaxies, and these are coming from different surveys. Now, since we mentioned that our fastest spacecraft have traveled less than the distance light travels in a single day, we need to note that everything we understand about the universe, whether it's studying the planets in orbit around other stars, or the structure of our Milky Way galaxy, or the mapping of intergalactic space like we're seeing here, we understand all of that by studying light. And we can figure out a lot. We can figure out the distances to these objects. We can figure out what they're made of. We can figure out how planets are forming around other stars. It's all amazing. And it's all informed by our study of the light traveling from these objects. Now, we're beginning to develop other tools, including gravitational waves and neutrino detections, but light is what's told us the most about the universe around us. And this becomes kind of an interesting conundrum as we travel farther from home. So again, we have clumps and clusters of galaxies. Here we're seeing two sort of interwoven surveys of the universe around us. Every one of these points, again, is a galaxy, much like our own Milky Way. And yet, you'll notice that there are many galaxies here or here. And it's not because there are no galaxies in the upper left or lower right. It's just that because we're using light to measure the distances to these objects and study them, if you can imagine the plane of our Milky Way galaxy, that spiral galaxy we live inside, it kind of coincides with these unstudied areas. And so the light from these galaxies is blocked, or at least more challenging to detect. So as we've surveyed the universe around us, we've focused on the areas that we can study best. And so we end up with sort of this hourglass or bow tie shaped collection of galaxies, not because the universe is shaped like a bow tie, but because those are the parts of the universe that we've mapped. So although we figured out a tremendous amount about the universe around us, there's still a lot that's inaccessible in certain ways because we're limited to the tools that we have, and we're limited by the light that can reach us and reach our telescopes here on Earth. So we're actually traveling far enough away that we're seeing yet another kind of object fade up. These are actually not even individual galaxies, but these sort of, I'm actually colorblind, but I think they're sort of peach colored circles. They represent quasars, the bright cores of young galaxies. We don't see quasars nearby because they occurred earlier in the history of the universe. Bright, these circles that are drifting by our in front of our camera view here are representing objects that just don't exist near us in the universe because they don't exist near us in time. And this is where that light travel time that I introduced you to early on really becomes mind-bending, because now we're so far outside of the human sort of scale of time that we're confronting the history of the universe in terms of light travel time. So we're looking billions of years into the past to see these objects and measure their distances. So we're actually confronted with this idea that looking out into space is looking back in time. Because light travels at a finite speed, a fast speed, but a finite speed, it means that whenever we look at an object far away, we're seeing it in the past. For the moon, it means we're seeing it as a second and a half ago. For the sun, 8.5 minutes ago. But when we look at distant galaxies or quasars, we're seeing them as they were billions of years ago. Now that's amazing, because that means that we can see the entire history of the universe played out in front of us. But it becomes a little mind-bending when we try to wrap our heads around how the universe has transformed over time, and we have to recognize that we can't get a snapshot of exactly what the universe looks like at any given instant. And the punchline to this is the sort of mottled kind of red image in the background here. That's actually the cosmic microwave background, which I alluded to early in the show. That is a baby picture of our universe. It's not an image like we saw of the satellite images of Earth. It's not like the galaxy that we saw earlier. Instead, this is sort of a high contrast heat map. The dark regions represent parts of the early universe that were relatively cool, and the brighter regions of the map represent parts of the universe that were relatively hot. And embedded inside all of this, we have all of these other observable galaxies and quasars in our sort of bow tie shaped collection of galaxies that are the galaxies whose distances we've mapped. The cosmic microwave background, though, this image, is actually super high contrast because the cool parts, those dark parts, are only 1 part in 100,000 times cooler than the hot parts, the bright parts. And that means that we've ramped up the contrast of these tiny fluctuations in the temperature of the early universe are revealed as this mottled image that we see as the backdrop to our galaxies. Now, turns out that temperature and density are related, so the bright parts, the hot parts, are actually a little bit less dense than the dark parts. The cool parts are a little denser. And those variations in temperature and density led to the formation of the clumping of galaxies that we see close to home. So there's a storyline that connects this cosmic microwave background to the galaxy locations and even eventually to the formation of our galaxy and our planetary system and life on Earth. This is the great cosmic story that astronomers are weaving together, and this map that I've shown you over the last half hour is one entryway to thinking about it. So with that, I'm going to go ahead and take us back home, and I've asked the computer to realign to make sure that we get home safely. And as we go, I just want to mention one thing, and that is something that's a little deceptive about the way we're displaying this. And it looks like we're at the center of the universe. That's a tempting thought. I know a lot of individuals who would love to think of themselves as the center of the universe, but in fact, it's not that we're at the center of the universe. The universe, as far as we understand it, has no center, but we're the ones drawing the picture. We're the ones mapping all of these data points. And so we end up at the center because we are displaying these in terms of their distance from us. So we are at the center of our map in the here and the now because we're the ones drawing the map. I apologize as I move through these. I think our streaming, I'm kind of hitting the limits of our ability to stream this well. So let me just go ahead and take my time moving back through our collection of data points that represent the quasars, those distant cores of young galaxies that we see in the past, but not nearby and not in the recent history of the universe. We're now zooming in toward the collection of galaxy distances that have been measured from surveys that have covered much of the sky, but not the entire sky because of limitations of ourselves living inside a galaxy that blocks light from distant parts of the universe. Now into galaxies that are relatively close to home. There's about 30,000 galaxies in this data set that are galaxies that have had their distances measured by really teams of astronomers working over a period of decades. And we'll move past some of the clumps of galaxies, including the Virgo cluster that's kind of moving away there from the center to the left-hand side of our image. And eventually we'll make it to our own Milky Way galaxy, which is just one of these points in the data set. Our own home galaxy with hundreds of billions of stars is, of course, a special galaxy for us because it's where we live. And it has that familiar spiral shape. We're going to travel in toward that marker representing the radiosphere, that sort of technological electromagnetic footprint of humanity in the universe around us. And as we kind of enter the radiosphere, I'll go ahead and fade it down. Just a reminder that the tens of thousands of the thousands of stars that we know to have planets are all relatively close to home, potentially being washed over, some of them, the nearest ones, washed over by our radio signals. And here, approaching our own sun, which again is shown as bright as the other stars, but as we get closer, we're going to dim it down a little bit so we can see the orbits of the planets around our sun. Our outer planets, Jupiter, Saturn, Uranus, and Neptune, the giants in the outer part of the solar system. And then here, the inner part of the solar system, Mercury, Venus, Earth, and Mars, the third rock from the sun, Earth. We'll go ahead and zoom back home, seeing the orbit of the moon around Earth, again, as far as humans have ever traveled physically out into space, although today in our virtual trip, we managed to travel much, much farther. So I want to thank you for being a kind audience here online, and hope you enjoyed our brief tour of the universe, and hope you'll have a chance to visit us in person at Morrison Planetarium and the California Academy of Sciences sometime soon. Thanks for tuning in.